All right, we're getting started. So I don't have this week's assignment up yet. That should be coming hopefully between this class and my next class. If not, it will be at some point today. You'll be implementing the sorts that we've talked about for your linked lists in an intelligent way that allows us to compose a linked list with a particular kind of sort. And that way you have to write each sort for each object, because that is very repetitive. And we've learned before, if we're copying and pasting code, there's usually something we can do about that. And in this case, that will mean we can write a new interface, a sorting interface, and then write 3 sort classes, and then compose a linked list of a sort type. So I'll explain that in the assignments. Maybe I should draw something out in advance, just to give people a little idea of what this is going to look like before we dive into implementing bubble sort. So we have our list interface, and we have our 2 or 3 different kinds of lists: singly linked list, doubly linked list, and circular linked list. And all of those implement a list interface. We're also going to now have a sort interface that is going to be the world's simplest interface. It's literally going to be one line. It's just saying that everything that implements this interface has a sort method. That's it. No other fields, no other methods, but we are going to have bubble sort, insertion sort, and selection sort all implement that interface. And so now what we can do is we can compose a list of a sort that says, now we could have something like, we'll add this to the list interface, and like a set sort method that can then take something of type sort. So one of these 3 types. And then we can now say singly linked list, whatever this is, list.sort, and it will take whatever sort is defined by that sort. So now we can switch the sort on the fly while we are running our code. We could even live get something from the user, have the user determine which sort they want to use, set that sort in real time, and then sort the list in that way without ever having duplicated this code or this code. So this is the strategy design pattern, if you haven't seen it before, but it allows for very nice scalability, because now if we wanted to add an extra list type, it would by default already come with the ability to sort it. When we go into advanced sorts, we could implement a new sort under this, that now all of these lists can be sorted in that way. With just a single implementation of that sort. You don't have to think about how does it work differently across the different list types. It will just work. So that's what we're going to be implementing for our next assignment. But what we're working on at the start of this class is implementing bubble sort. So take a moment and refresh yourself on what bubble sort is doing. We're just repeatedly comparing neighboring elements as we march down the list. When we find 2 that are out of order, we're going to swap them. Once we finish that process, we go back and do it again. We go back and do it again. We go back and do it again. The dumb version of bubble sort does this n times. The smarter version of bubble sort has this swapped variable that is going to keep track of have we made a single change. Rather than stopping once we've done this n times, we're just going to continue to do it until we don't make any changes. Once we don't make any changes, we must be done. So then take a stab at this in pairs, groups of 3, something fairly small. Don't go larger than 3. If you want to work by yourself, that's fine too. But see if you can seek out somebody, and maybe it's someone you haven't worked with, and that's probably a good idea, considering you will probably be taking future classes with these people, and it's a good idea to know who they are.
Yeah, there's a zero.
What?
Yeah, so it's not really. So should we do? You don't start at zero for this one, right? You start at one.
You want to start comparing 0 to 1.
Okay, but should you start at one and compare it to zero, or should you start at zero and compare it to one?
Does not matter.
Okay.
Can work either way.
I've never done solid source before, so I can see how big the box and thing works. Right. As we my dog's boss. Starts inside of it. After that, I'll be about her doing that house.
How are we doing? Were we able to get this working?
No.
Not quite yet. We have basically pseudocode that maps almost directly to Java, so I'm curious. So we have different levels of pseudocode across the different sorts, going from easier to convert to Java to harder to convert to Java. I feel it's probably the easiest one is for Java. Give you a few more minutes. Week 4 is
Four. So that makes it 6 weeks left. So actually.
It also means the 8th is next week.
I don't want that reminder. Thank you. I really appreciate it.
With every positive in life, there is an equal and opposing negative, and I'm here to remind you of that fact.
Thank you.
Yeah.
Colon equal.
That just means assignment. So it's assign swap to be true, or assign I to be 1,
Got it.
or I equals 1.
Same as just straight equals.
Yeah.
There's grades is from cycling, what goes down.
Mm-hmm. Life is cyclical. Life is sick. As in germs, and also sick is awesome.
Positive thoughts. Positive thoughts. Computer science will not make me a pessimist.
Good luck with that one. I'll be around when computer science breaks you. Same.
There's either mix of.
Lost my sanity a long time.
Me too. Stepping down.
Yeah, crazy. Quarters are fast.
I'm glad.
I don't think the 8 will have this.
I'm not great at marathons, so I tend to burn out about
I
half.
don't get
Semester. But quarters, since there's like, you have to stay far from the pace. Sprint. And then we're gonna get there.
Is it marathon or not sprint?
Quarters are sprints.
I'll just like, go all at once, and then I'm like dying for 4 miles. I like to think that is like, almost like, these are two illustrations.
Absolutely.
Yeah.
It's amazing what people will complain about. My first position was in Billings, Montana. No one there would shut up about the traffic.
It's kind of the things here, honestly, at one point, you can figure out the traffic is so bad, or like, one traffic.
There's no traffic here.
One traffic.
And Billings had maybe 1/4 of Spokane's traffic.
That's
Maybe. Maybe.
I got that part.
Oh no, you stopped behind another car at a red light. Traffic is awful.
I've been like, there. That's awesome.
Yeah.
I have driven. Next time I went to buy something, just such a
My favorite experience was Chicago during rush hour. I-90 from Chicago right through downtown during rush hour.
Why are you making it a blue?
It's either true or false, right? We've either made a swap or we have not.
And typically, it's one question.
You could,
Whatever we do.
underneath the hood of it, it is just an int. Yep. It also allows you to make statements like this,
Yeah, so.
which is pretty readable, well swapped. As opposed to if you have something like, well, swapped equals one, or well, swapped equals zero. I find that to be a little bit harder to read. So what does that mean? What is one here? What is zero? You could reasonably make one true and zero false, or zero true and one false. You have to look deeper into the code to figure that out. So the first thing we're gonna do inside, we're gonna set swap to false. Because we haven't actually swapped anything yet. Once we do that, we're gonna go into another loop, but this loop is going to be comparing each one of the values adjacent to each other. So we're gonna start looking at index 1 and look backwards, but it is perfectly valid to start at index 0 and look forwards. Either one of those will work. All right, so starting at index 1, going until we reach the last element, which is the last element before the size. That will be the last element that we want to compare the element before it to. You'll make fewer off by 1 errors if you start at 1, because you know that 0 exists and you can go until you reach the last element. If this started at 0, you would want to go well less than list.size minus 1. I find that ever so slightly harder to think about. Not too bad, but it allows us to make this. So now we want to say if they're out of order. How would we say they're out of order?
Array dot get at I minus 1 is bigger than array dot get at I.
Yeah. If the one that comes before, the one before this element is out of order, which means it's greater than. Let's not get of I. Then we want to swap them. Let's use our old triple swap with a third variable, because why not? We'll say this value temp is going to be set to the value at I minus 1. You could say I here and do it the opposite way. This is just a triangle. You still have a triangle regardless if the arrows point in a counterclockwise or a clockwise direction, as long as all of them are facing the same way, if that makes sense. So if we're swapping between 3 variables, we have temp, we have I minus 1, and we have I. So we could either do something like this, and then this, and then this. So that creates a triangle in a clockwise direction. Or we could do, we're going to store this in temp first, then this, then this. And that's more of a counterclockwise direction. Either one of those will work. So there's nothing wrong with either of those. We're just going in we're going to start by writing, what is it? I minus 1 into temp. So we're doing this clockwise direction. Then we can say list.set. The index we want to set is the index we just stored. So we're going to set it index I minus 1. We want to set it to the value of the other one. So we want to list.get I. Finally, we want to set back I to be temp. So that'll complete the swap. Any questions on anything you've written so far? Yeah, the order of this.
Yes.
So there are 2 that will work. The other that would work would be the other way in that triangle. So we can say get I, now set I to I minus 1, and then set I minus one to temp, this will also work. So,
Do we have to set the first one to set has to be the one just?
yes. Yeah, otherwise you get two different copies in the same, in the two different locations, and you've lost one of the values. So we just need to make sure that we always have access to those values, but either one of these three line segments will work. Okay, so we've completed the swap. Once we do that, we want to make sure we set swapped to true. Because we made a change. This will allow us to loop back around, reset swap to false once we complete this pass. So this is just going through each pair. And we want to continue doing that while we're making at least one change. As soon as we fail to make one change, we will fall out of this while. But the array is sorted. The list is sorted. So let's test. I'll just grab our exact same main out of any of our other sorts. Make sure it works by calling bubble sort. Sure enough, that also sorts the list. So there are still actually improvements we can make to this. Can anyone see any way to make this process faster? It is not faster in terms of the order. But there is an improvement that we could make. It's not a small change. It would involve gutting this good chunk and rewriting it a little bit, but it's the same idea of comparing adjacent elements. Think about that for a couple minutes. I'll give you the hint, we don't need swapped. What did we say happens, we know for sure, after the first pass through this outer loop?
Wouldn't it be the largest number in our array?
Yeah, the largest value is in the last spot.
Yeah.
After the second pass, what can we say about the structure of the array? Second largest value is in the second largest place. Is there any reason to ever compare the values of the second to last place with the last place ever again? No. Are we doing that in this code? Yes. We're going all the way through the array every time. So wouldn't it be nice if we could identify where we could stop the comparisons, because we know that there's no way that the new value is ever going to be larger than any value after where we are in the list. So we are going to write an improved bubble sort that does exactly this. So I'm going to start with the bubble sort code. And from there, we're going to get rid of swapped. And I'm going to call this something like, and in fact, I don't think we need this or this or this. We do need some condition on this while, though. So we're going to have some kind of variable we're storing off to the side that is a placeholder into the array that says everything after this must be sorted and larger than anything else that is left in the list. So we're going to make some, what do I want to call this?
And
We can just call it in if we want to. We're just gonna start it out as the size of the list. Saying that nothing is in place, nothing beyond this exists, but if stuff were beyond this, then it would be sorted. And then we can say while n is greater than 0, capital N, well, n is greater than 0. We're gonna do something. When we make any of these changes, what do we know about n at this point? Would we agree that the last swap that we make, whenever we make that last swap, everything after that is in order? Each pass through the loop. So when we make a swap, let's set something. So we're going to, before we jump into this loop, we're going to make another value that is the new value that this n is going to have when we are done with this. So I'm just gonna call this new n. This is not typical Java syntax for a variable, but it will work. And we're gonna set this to be 0 to start. And when we make a change, we're going to say new n is this I, the last position that we made a swap at. And then when we are done with this for loop, we've gone all the way through the array, new n is going to store the index of the last swap that we did. So now we can set n to be that value of new n. This should keep us from making unnecessary changes or unnecessary comparisons with something that has to already be in order. So if we run this, we see it still sorts the array.
If it bubbles all the way down, could you not just bring it in?
Yeah, but we would notice that as we're going all the way through the list, we would say that the last value that we're doing here is that value. I guess, yeah, we probably want to. You only need to do this. Rather than list.size, we really only need to do this up to n. That should still work. That actually saves the work. Yeah, so this n is keeping track of, let's draw out maybe an example of this in action. No, action, not inaction. So random numbers, shout out.
27. 5.
You can count. 13.
2,
2 more.
24.
1 more. Perfect. All right. So we're going to make some changes. We know we're going to grab the largest value and we're going to move it to the end. So what we're storing now is we're starting out this value of n as the size of the list. So let's say n is, we have 6 elements in this list. And new n is we're storing this value that is the last place that we swap when we do this. So we know when we compare 27 to 5, they're going to swap. We know 13 is going to come here. You know 2 is going to come here. We know 24 is gonna come here, we know 8 is gonna come here, and we have 27 at the end. That last swap that we did. With that value I that was 5. Instead of nu n being 0, nu n is going to be 5. And when we finish this pass through this inner loop, we're going to set this value of n to nu n. So this becomes 5. And this tells us we don't need to make this comparison ever again. This 4 and this 5 are in order relevant to each other, relative to each other. We need to make every other change, but we know since the largest element is in 27, we don't need to compare that to anything else because there's no reason that will ever swap. So when we loop back around and just say I is less than n, now n is 5, so we're only going up to 4 and not the 5 that we did before. So let's go through, no change. 13 and 2 will swap. The 24 will go here. No, well, 13 stays here. 13 stays here, 24 and 8 will swap. Since that last swap happened here with I pointing at 4, nu n in this case is going to be 4. So n becomes 4. And now we see that 4 and 5 are in place. And we never need to compare anything to 4 and or anything to 5 ever again. So this does not actually change the order of running for bubble sort, but it does allow us to have the work. On average, this will run about twice as fast. Yeah,
If we're talking about optimization, why would you do nu n instead of n minus minus?
because it is possible that things are so in order that, for instance, let's look at what happens if an array is in order. So we have 1, 2, 3, 4, 5. We go through this first pass and we make no changes. Nu n never got modified from its original 0. We said n equals nu n and we're done with a single pass. So it allows for whenever there is a portion of the array that is in order when you go through this process, or when you do a swap, it creates more than one that's in order. We start skipping all of those the next time through. So it actually does improve the best case as well as the average case by about a factor of 2.
So when you have nu n set to I, basically, it keeps track of the last thing that was swapped. So
Yes.
like, if 5 and 2, but 13. Through everything else, it was all, every 0 and 1 were wrong.
Yeah,
Everything else was sorted and go through it once, and then it'd see that 0 and 1 was the last thing that was swapped, and then it'd start from there.
yeah. So it only look at 0 and 1 in the future to say, do we need to make this one last swap? Everything else was in order.
Okay,
Yeah. So the improvement, yeah, looks for portions of the array that are in their correct positions as we do this, and then says, we don't need to look at that ever again because we know it's in order.
what if 2 things in the middle of the list are in order, but things after that are not?
That is fine, because when we compare that to adjacent items, we'll be making those changes later on in the list.
Okay,
If it ever gets to the point that everything at the end of the list is in place and those elements didn't change where they were, then we could skip 2 spaces at once, which would skip an entire pass through this inner loop at that point.
Okay.
Great questions. That makes sense? Questions about improved bubble sort? Let's analyze the complexity. So in its base form, what do we have for a best case, a worst case, and if we can, if those are different, an average case? How is this scaling with the size of the list? Yeah,
Let's say that you have at least bare minimum
Is it that while is we're gonna have to happen like at least and square times?
Yeah,
Yeah.
yeah, just like every other method we have seen for sorting so far, this is quadratic in the worst case,
Linear in the best case.
is it?
Yeah. I don't know from what I see.
So if the list is completely and totally in order. Maybe that's the best underlying case for this. What happens? We set swapped to false. We go through and we don't make any changes. We go all the way through the list. We don't make any changes at all. We never set swap to true. The while loop ends. Seems linear to me. So now we have to ask the average case question, because the best case and the worst case were different. So on average, how much work are we doing? Is it proportional to the square of the size of the list or proportional to the size of the list? Or somewhere in between?
I would say we, once again, if the thing of you're more likely to have a randomized list than you are going to have a perfectly sorted list.
Yeah, how many bubbles do we expect to make on a given pass through the? Basically, how frequently do we expect to make at least one swap? Because if we do that, then we have to look back through the entire list again. The only way we don't make a swap is if everything is in order. We can only stop this early if this process makes everything in order. Which is very unlikely. It becomes more and more likely as you get closer to the end of the list. But that would save you one pass through this loop, and not something that would shave it down to just one pass through the loop. It would save you one pass through the loop. So because of that, the average case is also quadratic. Yeah.
Could you explain then how we get in square?
Yeah, so. We're going through this inner loop. Let's look at the inner loop first. So we're comparing every adjacent pair of elements. How many adjacent pairs are there from a single pass to that loop? N-1 pairs. So if we have a list of size 7, we're going to compare index 0 to 1, 1 to 2, 2 to 3, 3 to 4. There'll be 6 of those for a list of size 7. So this is going to run N-1 times every time that it runs, since it's comparing every adjacent element. And now this is going to run, this whole inner loop is going to run as long as we make a single change to the list. Another real question is just how frequently are we making at least one change to the list? And that's unless the list is already in order, the answer is we're always doing that. So in the worst case, we have to look at this for every possible value. If we continue to do this process, we get just the largest value in the last place. Just the second largest value in the second last place. So we're going to do this process n times. So since these are nested, this 4 is inside of this while, you'd have n times n-1, which is quadratic, n squared minus n. In the best case, the list is already in order. So since this is already in order, we never set swap to true. We loop back around and swap is false. So in the best case, this runs once. 1 times n-1 is linear. But now in the average case, it's a little bit harder to figure that out, a little bit more work to ask yourself, when could we stop early? Are we likely to stop early after a constant number of passes through this loop, like 1 or 2 or 3, regardless of the size of the list on the average case? Or are we likely to run through this loop n times, or n-1 times, or n-2 times? So is it based on the size of the list, or is it based on some constant number of times regardless of the size of the list? And it's more so the size of the list. Yeah. So it's more likely much more likely to be this on average, or some value that's close to this. Maybe you get an n-1 on average. Questions on that? All right. This is the end of basic sorts. So I will upload all of this code and get the assignment out with instructions so that you can take everything that we have done so far and implement it for your linked lists. Now, note that for everything that I have done, I've assumed this is an array list. And I've done that on purpose, because now you need to interpret and think, how do we do every one of these elements with a linked list, with the functionality that we wrote? There is no list.get, list.set exactly like this. Or is there? Since it adheres to the same kind of list, can we just almost copy and paste this? Intriguing. I'll leave you to think about the amount of work that this is going to be to get this to work with a linked list, to get that structure up for a strategy design pattern, and we'll go from there. I'm sure people will have some questions as they get started. But we're going to transition to a very important topic.
Are all of your slides uploaded on Canvas?
Since we've now finished the sorts, I will upload the sorts one. I basically, as soon as we're done with a slide deck, then I upload them. But yes, they're on Canvas under modules.
Alright, cool.
All right, so recursion, just getting a sense of where we are. Who knows what recursion is? You've seen it before in some capacity. For whom is this a brand new topic? Again, just trying to get a sample of where we are. There's no shame whatsoever, and I don't really know what recursion is. Totally fine. So we'll start motivating this with the easiest example that I can come up with, which is that you're standing in line for the most exciting thing in the history of ever. I'll let you decide what that is. Whatever the single most exciting event that you could be at that would just make you the giddiest to wait to be in, to experience this thing that you're in line for. But unfortunately, the line is really long. In fact, it's so long that you can't see your position in the line. It bends around the block, around the corner, and you don't know where the venue is or whatever it is that you're trying to get to. There's an unknown people in front of you, but you really want to know how long it's going to take you. Maybe there's an idea of, I think they can admit 10 people per minute. How long is it until I get in to this most exciting thing in the history of ever? Unfortunately, you can't leave your place in line to go count the people in line. So you need to use anything that you have at your disposal to figure out how many people are in front of you. Those of you who have heard of recursion before, what's the answer? How do you figure out how many people are in front of you without leaving the line? Yeah? Yeah, you turn to the person in front of you, tap them on the shoulder, and you say, hey, I'm curious how many people are in front of me. Could you tell me how many people are in front of you? And of course, that person in front of you is in the same situation you're in. I have no idea how many people are in front of me, but they could do the same thing that you just did. Tap the person in front of them and say, hey, the person behind me needs to know how many people are in front of them. Could you tell me how many people are in front of you? This exact process carries all the way down the line until magically there's this person with no one in front of them. They know how many people are in front of them. The answer is 0. They turn around to the person behind them and they say, there are 0 people in front of me. That person goes, great. I probably could have seen that, but I asked you anyway. They get back that response that is 0. And they know from their own perspective, there is 0 plus 1 person in front of them. So they can turn around to the person behind them and say, there is one person in front of me. That person can interpret and say, all right, well, if there's one person in front of you, there must be two people in front of me. They can turn around to the person behind them, and back goes the message chain all the way until it gets back to you. And suddenly, you know how many people are in front of you without having left the line. Does that make sense? So taking this idea, you can break it down into these steps from your own perspective and turn this into an algorithm that can work for any particular person in that line. You basically are going to ask the person in front of you, how many people are in front of you? Then you are going to wait. When the person tells you, you are going to add 1 to it. You agree that this is really the only steps to this problem? From your own perspective. Yeah, there's a lot more work that's happening from other people's perspectives, but from your perspective, this is the entire amount of work that you have to do. Ask the person in front of you how many people are in front of you, wait, whatever they tell you, you add 1 to it. And if you weren't the original asker, then you turn around and report that information to the person behind you. That's how much work it is for any individual person in the line. This is not quite the case if you are the first person in line. If you are the first person in line, you instead just you're the first person in line, this is what you do. So this process allows you to basically break this down into the 2 components of, if you're not the first person in line, do this. If you are the first person in line, do this.
Does it matter if you're the last?
Nope. If there's no one, you have to have been the original question answer if you're the last person in line. There's no one to turn around to. You wouldn't have been asked by that person behind you because there's no one behind you. So if you've heard of the concept of a base case and a recursive case, this is your base case. This is what stops this process from being infinite. And then this is your recursive case. No one in this recursive case can answer the question by themselves. You have to funnel all the way down to the base case, and then they respond back to you. If you're trying to think of this as some kind of diagram, then you have this very long line. There's going to be the asking process until we get to the base case. They have an answer, and then the answer propagates back through the line. You can also think of this as going down to a base case and then going back. So you go down to the base case and then back through the recursive case. So note that this wait, you can't do everything after this until the person in front of you responds. So the how many is what goes down this line. How many, you get the base case. Add 1, add 1, add 1, add 1, add 1. So recursion is not particularly scary if you think about it in terms of breaking into these components. What are you, in the recursive case, what are you doing before, like, how do you set up the problem for the person in front of you? Wait for a response. What do you do when that person responds to you with that information? How do you crunch that information or prepare it to pass back to the next person? And in the base case, you already know the answer from your own perspective. So we'll see that this outline works for every recursive problem. It can be broken down into exactly these steps. Some of these steps will have nothing in them sometimes, but you can think of any recursive problem as exactly these steps. What do you do in advance? What do you do in return? And in the base case, how do you set up the base case that already knows the answer? So we will explore lots of problems like this tomorrow. I'm hoping to have exams to hand back to you tomorrow as well, so we'll probably go over the exam, and that may take the entire class, we'll see. But if not, we'll dive back into recursion.